This is chapter 4, section 2. We're going to do this in 2 separate lessons. So this is part A. What derivatives tell us? So to do this, we've got to understand what some definitions here. So increasing and decreasing functions, what is that? We're going to read through this together. Suppose a function is defined on an interval I. So I is just like a starting point and an ending point. That's an interval. Here's an I from here to here. So you just define it on a domain. What does it mean to be increasing? So a value of the function at one point must be greater than the value of the function at another point whenever x2 is bigger than x1. What does that mean? As you move left to right, the point to the right of any other point must be bigger. If that happens for all values of x, all x2 bigger than x1, then it's increasing if the point to the right is bigger than the point on the left. And similarly, if the point on the left is bigger or smaller than the point on the right is smaller than the point on the left, you are decreasing. So let me give you a visual picture. They're saying x2 is bigger than x1. So if you pick any x2 and any x1, that point and that point, what's that point? That point is f of x1. This point is f of x2. So we're saying if f of x2 is bigger than f of x1, then the function is increasing. So I think you have a good feel for increasing. This is all you have to realize. Increasing and decreasing is dependent. You're moving left to right. If the points are getting bigger, increasing. As you're moving from left to right, if the points are getting bigger, it's increasing. And here, you have an x1 and an x2, and they could be anywhere as long as x2 is bigger than x1. That would be f of x1. That would be f of x2. And they're saying if f of x2 is smaller than f of x1, f of x2 is smaller than f of x1, then you are decreasing. As long as you pick 2 points where x2 is the right of x1. So as you move left to right, decreasing. Left to right, decreasing. Now here's why you can get confused if you understand you're moving left to right. Some might say, what's this function doing? Is it increasing or decreasing? You say, oh, that's decreasing, it's getting smaller. No, it's increasing because you don't move right to left, you always move left to right. As I move left to right, it's getting bigger. And somebody say, what's this function doing? Is that increasing? Look, it's getting bigger. No, because you always go left to right. As I move left to right, it is decreasing. So, yeah, I think you have a good feel. Increasing, decreasing, always moving left to right. Here is the big theorem. And this is actually pretty easy and pretty intuitive, so please don't memorize this. It should make total sense, and I will do a visual example. So all this is saying, you don't have to worry about all this up here. If the derivative is positive, greater than 0 is positive, if that's true, then the function's increasing at those points. And if the derivative is negative, then the function's decreasing at those points. Please don't memorize this. I'm going to do a example for you. So we have a parabola. Now let's look. What is the derivative? You have to know the derivative is the slope of the tangent line. And what that, let me get back to this. This is saying if the derivative is positive, meaning the slopes are positive, then the function's increasing. Well, let's take a look. Look, the slope of that line, the blue line is a tangent line, is positive. But look, the function's increasing all the way from there to that maximum point there. So look, everywhere from that point on to the right to that point, the function is increasing, but look, all the slopes are positive. In other words, the derivative is positive from there to there. Now at the top, the derivative is 0. It's neither increasing nor decreasing at that point. But as you move to the right, the slopes become negative. All the slopes are negative to the right there, but the function is decreasing to the right there. Let's look at this one. Okay, what do you notice about the blue slopes? The blue slopes are all positive from there to there. They all have a positive slope because it's moving upwards, but the function is increasing on that whole region. Now, the derivative is 0 here. To the right, look, all these slopes are negative. From there to there, the slopes are negative. But what do you notice about the green function? The green function is decreasing everywhere where the blue line has a negative slope. And to the right of that, the slopes are positive. And what do you notice? The function is increasing to the right of that. So that should get you a pretty good feel. We'll do this one again. Look, the slopes of the blue line, which is the derivative, the slope of the tangent line is the derivative. The slopes are all negative, so the derivatives are all negative from there to there. But the function is decreasing from there to there. Look, the slopes are all positive. The function is increasing in this region. So you shouldn't have to memorize that. Look, positive slopes, increasing function. Negative slopes, decreasing function. And positive slopes, increasing function. So you should just visualize tangent lines of an increasing function and see that it's positive when the function is increasing. These are musts, so you'll be quizzed on all these things. Now this you really won't be quizzed on, but Theorem 4.3, very important. When the derivative of a function is positive, at that point, the function is increasing. When the derivative of a function is negative, at those points, the function is decreasing. All right, we're going to do an example here. Sketch a function with the following conditions. So we're going to do some things that are easy. F of 0 is 3. I can do that. F of 0 is 3. Oh man, this graph is backwards. Sorry about that. I don't know how that happened. Okay, and then we're told f of 4 is -1. I can do that. 4, -1. And then 8, 7. F of 8 is -7. 8, -7. I apologize, my graph got flipped somehow. So those points, we have taken care of these three things. Now, I'm going to make a chart. This will be -infinity. This is infinity. And we have special points, 0, 4, 6, and 8. 0, 4, 6, and 8. And those are my x values. But look what's happening. Let's read this. From -infinity to 0, the derivative is positive. So we know the function is increasing. And then from 4 to 6, the derivative is positive, so the function is increasing. And then 8 to infinity, the derivative is positive, so the function is increasing. Now from 0 to 4, the derivative is negative, so on that whole region, the function is decreasing. And then from 6 to 8, the derivative is negative, so we know it's decreasing on that region. So we have this general increasing, decreasing, increasing, decreasing, increasing general shape of the function. So we've evaluated these two things. Now we have to start drawing this. So up to 0, it's increasing. So from -infinity to 0, it's going to be going up. I don't know if it's going this way. I don't know if it's going this way. I don't know. But I know at 0, the derivative is undefined. So at this point, well, let me go back. The function is continuous. So very important. It is continuous. So for some reason, the derivative doesn't exist at 4. Well, it's not a discontinuity. We're told it's continuous. So either it's a vertical tangent line or it's a sharp point. I'm going to make it a sharp point. I don't know what this looks like, but I'm going to do this. This is one possible answer. So the function is increasing, but then after that it's decreasing. So I need to decrease from here to here, but the derivative is undefined at 0, so I need a sharp point right there. So I, for fun, am going to do this. Now, you say, why do that? How come it's not like this? It could have been like that. It could have been like, no, it couldn't have been that. It could have been a straight line. Yeah, you could have drawn a straight line, possibly. Okay, but we're doing a graph. There are multiple answers. Now, from 0 to 4, I'm increasing. Or decreasing, sorry, decreasing. From 4 to 6, I'm increasing. So here's 6. I have to increase. But what's happening at 6? Okay, this is important. The tangent line has a slope of 0. So I have to have a flat tangent line. So that forces the shape of the function at this point. It's got to be a slope of 0. So it's got to be looking like that, and that's kind of ugly. It's got to be like that, where the tangent line at that point has a slope of 0. So that forces my graph to be like that. Now that could be, again, a straight line, a curved line. It's just got to be decreasing. It could change shapes twice. We don't know, so you can do whatever you want. So it's going to be increasing from 4 to 6. So I'll do that. It's increasing. I don't know where it ends up at 6, but at 6, okay, here we go. At 6, the tangent line has to have a slope of 0. So I need a curve flat again, so I need to fix that. So at 6, it's got a curve, and the tangent line there has to have a slope of 0 again. That's why I made this nice curve where the tangent line has a slope of 0. And then we decrease from 6 to 8. So from 6 all the way to 8, I need to get to that point because they told me it's continuous and it's -7 at 8. Now look what happens at 8. It's undefined. That means I have a sharp point there. And then from 8 to infinity is increasing. So I don't know, you can do whatever you want to the right. I just did that to show you. You don't know what it looks like. As long as it's increasing to the right of 8, you're good. And that fits all of our conditions. So this is one example. We're going to have a whole worksheet coming up where all you do is practice these. Let's keep going. Find the intervals where the function's increasing and decreasing. Well, we learned increasing and decreasing is determined by the first derivative. So let's find the first derivative. Now, this is a product. We're multiplying two things. And not only do we have a product, that's not x. That's a function, so it's box. So the derivative, leave the first alone, take the derivative of the second. Well, the derivative of e to the box, I am my own grandpa, but you need to multiply by the derivative of box, plus the derivative of the first one is 1, and you leave the second alone. So we notice they both have an e to the x, or minus x. I'm going to factor that out, and I'm left with minus x plus 1, which I can rewrite it like this. Okay, so here is, okay, I didn't tell you this. Did I put the graph in? Okay, I did. Oh, never mind, my brain. Okay, we're good. So here is an important thing, and I will show you this. I guess I should hit this now. What defines a point where it changes from increasing to decreasing? Okay, that's where it changed from increasing to decreasing. And here, decreasing to increasing. So that's a point that defined where it changed. And then increasing to decreasing. That's a point that defined a change from increasing and decreasing. So here is your next important thing. For something to change from increasing and decreasing, okay, I'll go back. No, let me go back here. In order for something to change from increasing to decreasing, looking at this, the derivative has to change from positive to negative or vice versa. So the derivative has to change signs. The only way a continuous function can change signs is if it equals 0 first. It has to equal 0 and then change signs. So we are going to set this equal to 0. In other words, 1 minus x will be 0, so x equals 1. Now the other place where a function can change from increasing and decreasing, a sharp point. So a sharp point is where the derivative is undefined. So we need to check any sharp points where the denominator equals 0. But look, e to the minus x never equals 0. How do I know that? Because I know the graph of e to the x. Looks like this. And I know that graph never touches the x-axis. So e to any power never equals 0. So all I have is one critical point at 1. So here's what we're going to do. The derivative can only change signs at 1. That's the only place. So I'm going to make a number line. Here's 1. Here's negative infinity. Here's infinity. And these are my x values, and here are my derivative values. So I'm going to pick any value between 1 and negative infinity. And I don't want to get crazy. 0 is easy number to use. And one number between 1 and infinity, I'm going to pick 2. Now we're going to find the derivative at that point. If you plug in a 0 here, 1 minus 0 is 1 over e to the 0, which is 1. So that's 1, but I know it's just positive. I plug in a 2. 1 minus 2 is negative. That's always positive because e to any power is always above the x-axis, so that's going to come out to be negative. Now, I'm going to remind you, at 1 is the only place where the derivative can change signs. Therefore, between negative infinity and 1, it's always either positive or negative. So I can pick any value between negative infinity and 1, and the derivative will always be positive. So I just happen to pick 0 because it's easy to work with. And since it's positive at 0, it's positive everywhere from negative 1 to infinity. And then, between 1 and infinity, the derivative is either always negative or always positive. It cannot change signs there because it can only change signs at the critical point, which is 1. If I plug in 2, the derivative comes out to be negative. Therefore, any number between 1 and infinity plugged in here will come out negative. So I'm good on that. So what's happening? The function is increasing here and decreasing here. So here's my final thing. This is where you need to write in proper English. So all this work is necessary that we've done so far. All of that is showing where the critical points are, because at the critical points are the points where it can change from increasing to decreasing, vice versa. Now, you shouldn't just memorize that. You should know that because this visual picture. Critical point, increasing, decreasing. Critical point, decreasing, increasing. Critical point, increasing, decreasing. It changes signs at critical points. Now, another note, just because you have a critical point doesn't mean it changes directions. It's increasing left and right. But if it's going to change directions, it's going to be at a critical point. Muy importante. Great quiz question. So here's my only critical point. That's the only point it could change directions. So this chart, if this were an FRQ, is part of your work showing where the derivative is positive, where it's negative. You have to know why I put the derivative. Why did I do the derivative? Because the derivative tells me increasing, decreasing. So you have to understand why this chart, why these numbers. If you don't, you're going to struggle with this. So please Go through this. If you're confused, ask questions. If you're memorizing, oh, I put f prime there, that's bad. You have to know why you put f prime, because we are finding increasing, decreasing. You should know increasing and decreasing is determined by the derivative. The derivative can only change signs at the critical points. That's why you check around the critical points. All right, so here's my final conclusion. F is increasing on the interval from negative infinity to 1, and you have to give a justification because f prime is positive on that interval. So you need to write all that out. That's your justification. And then f is decreasing on the interval from 1 to infinity, and you have to give a reason. We can write shorthand because f prime and is negative. So I'm going to put less than 0. So you can write is negative or less than 0 on that interval. And again, I need to say where it's negative. I can't just say because it's negative. Could I say, oh, it's increasing on this interval because f is negative? No, I can't say that. Or can I say f is decreasing from negative infinity to 1 because f is negative? No, it's decreasing from negative infinity to 1 because f is positive from negative infinity to 1. So you have to say where the derivative is negative to justify why it's decreasing on the interval. So very detailed, but that's required on an AP test. And to evaluate what's going on, we found our only critical point to be 1. That matches with that. That's the point where the tangent line has a slope of 0. And we found it's increasing from negative infinity to 1. Bam. And it's decreasing. It's going down to the right of 1. So 1 to infinity is decreasing. So it matches our graph. That's what's happening. We found one critical point where the slope of the tangent line was 0, right there at 1. That's what we did there. Here's our next example. We're doing the same thing. So I need to find the critical point. So I need to find the derivative, which is 6x squared plus 6x. And I want to know when that's 0. I factor out 6x, and I get x minus or plus 1. And I set each of these equal to 0. And I get two critical points, 0 and negative 1. So those are the places where the function can change, increasing, decreasing, vice versa. So I'm going to make this table again. And this table is a number line. I have negative infinity on the left, infinity to the right. Negative 1 and 0 are my critical points that I found. So in this region, it's either always increasing or decreasing. Same with that region and that region. We have 3 different regions where it can be increasing or decreasing. Remember, it can only change directions at critical points. So only at these points can it change from increasing to decreasing. So that's why on this region it's always the same. On that region it's always the same. On that region it's always the same. Now, why do I put the derivative here? If you get confused whether to put f or f prime, you have memorized and you don't know what you're doing. What tells us increasing or decreasing? The derivative. That's why we find the derivative there. Pick any number. I'm just going to pick random numbers that seem like that are doable. So I need to find f prime at negative 2. You know what? I'm going to move this over here, because that's the point I'm evaluating. Now, you could plug it in 6 times negative 2, negative 2 plus 1, and get the actual value. What would that be? That would be negative 1 and negative 12, positive 12. Now, it's positive in that region. You don't have to actually calculate that. Watch. This is negative because I'm putting in negative 2. That's negative. Negative 2 plus 1 is negative, and two negatives make a positive, so I know it's positive. You don't have to find the value. Just know it's positive. Now I'm going to plug negative 1/2. That will be negative. Negative 1/2 plus 1 is positive. A negative times a positive is negative, so I can say it's negative there. Now you can find the actual value at negative 1/2, but that's just work. That's not necessary. You want me to do that? I don't know. What is that? Negative 3 times 1/2. That's negative 3/2. But that work is not necessary. We just have to know it's negative. And we know between these 2 points it's always negative because it can only change signs at the critical points. I'm saying things over and over, but it's very important. Now we need to know f prime at 1. And I'm not going to calculate that. I just know when I put a 1 there, that's positive. And a 1 plus 1, that's positive. So it's always positive, so I know it's positive. Okay? All right, here's my final evaluation. I'm going to say f is increasing on 2 intervals, there and there, because that's where the derivative is positive. So I'm going to say on the interval from negative infinity to negative 1 and from 0 to infinity, and I need a reason, because f prime is positive on those intervals. I need to say where the derivative is positive on those intervals. And then I can say f is decreasing on the interval from negative 1 to 0, and the reason because the derivative is negative on the interval from negative 1 to 0. Now, let's look at the picture so we can make some connections. We found critical points as 0 and negative 1. Well, there's a critical point, and there's a critical point. What did we find there? The derivative was 0 at those points. Look, tangent line, 0. We found increasing from negative infinity, negative 1. Look, increasing all the way up to negative 1. From negative 1 to 0, it's decreasing. That's what we found. And from 0 to infinity, it's increasing. That's what we found. So that fits nicely. Let's keep going. We have more stuff. All right, remember we introduced relative max and min, or local max and min? So I have a graph, and we're going to have something called the first derivative test to find relative max and mins. So let's process this. Look, there's a relative max. It occurs at a critical point. Here's a relative min. It occurs at a critical point. Here's a relative max. It occurs at a critical point. Now, we learned that all relative max and mins always occur at critical points. But then, this is the other thing that you need to know and be quizzed on. Just because you have a critical point doesn't mean you have a relative max or min. Here are 2 more critical points where the derivative is 0, but there's no relative max or min. So, here's the conclusion. All relative max and mins occur at critical points, but all critical points are not relative max or mins. So if you're looking for relative max and mins, you're going to look at the critical points. But just because you have a critical point does not mean it's a relative max or min. We have to test. And that's what theorem 4.4 says. So you have a continuous function, and you have critical points. So at those critical points, if the derivative changes from positive to negative, then there'll be a relative or local maximum. If the derivative changes from negative to positive, then you're going to have a local minimum or relative minimum. If the derivative does not change signs, it's neither a local max or min. Now, please don't memorize this. Watch. Positive derivative, negative, negative. Look, when the derivative changes from positive to negative, you have a relative max. Look here. The derivative is negative, derivative is positive. When the derivative changes from negative to positive, you have a relative min. Look, positive slope, negative slope. When the derivative changes from positive to negative, you have relative max. Here, positive slope, positive slope. When the derivatives don't change signs, you have neither a relative max or min. So please don't memorize. Have it make sense. Positive slope to negative, relative max. Negative slope to positive slope, relative min. So in other words, when the derivative changes from positive to negative, you have a relative max. When the derivative changes from negative to positive, relative min. So the first derivative test, very logical. Don't memorize, visualize. Again, that's a relative max because the derivative changes from positive to negative. That's a relative min because the derivative changes from negative to positive at that point. Okay? And you need to be specific at that point C when we do these. So here's my first example. Now that graph's not going to be given to you. This is what's given. This graph we're going to look at later to find out how this works. Okay, so finding increasing, decreasing, and finding relative max and mins are all tied together because, I'll say it again, it's at this critical point where it changes from increasing and decreasing, yet it's at that critical point where you have a relative max because the derivative changes from positive to negative. Okay, now be careful. Some people say, oh, there's a relative max there because the derivative changes from increasing to decreasing. No, the derivative changes from positive to negative. Do not say from increasing to decreasing. The derivative is not changing from increasing to decreasing. The derivative is changing from positive to negative. Now, what is true, the function is changing from increasing and decreasing, but that is not the justification for a relative maximum. The justification is the derivative changes from positive to negative, not the function goes from increasing to decreasing. Those are common mistakes that people make. So do not make those. It's a warning for you. So where can it change from increasing to decreasing, and where do I find my local extrema? Those happen possibly at critical points. So we need to find the derivative. So that should be pretty easy, hopefully. I'm going to factor out a 12. Oh my. Can you guys factor this? I might do a long division to factor this. Divide this by x minus 1 or x plus 1. I'm not sure what it's going to be. But on an AP test, you're never going to have to do this. But for these homework, it's going to happen sometimes. So we're going to have to figure out how to factor this. I'm going to cheat and make sure in the book that I choose the right one. So I could do a -1 or positive 1, actually. It has to be -1, positive 1. This is going back to what we call it, pre-cal. We did this at pre-cal. Remember synthetic division, 1, -1, -1, 1. And I'm going to try a root of -1. That's going to come from x plus 1, has a root of -1. Bring down the 1, multiply, add those, multiply, add those, multiply, add those, 0. So my remainder is 0. I'm left with x squared minus 2x plus 1. And so this factors to 12, x plus 1, and my quotient. Now, again, on an AP test, you will not have to do this, but that's something you should remember from pre-cal. So x and x gets my x squared, 1 and 1. I need minus minus. That is my final factoring. Now, critical points is when this equals to 0. So it's when x plus 1 equals 0 or x minus 1 equals 0. So I have a critical points of -1 and 1. So those are the points where magic can happen. So I'm going to do my number line. And I have two critical points, -1 and 1, and -infinity to infinity. And again, if you don't know why you're putting the derivative there, you're memorizing and not understanding. The derivative tells me increasing, decreasing, and not only that, when the derivative changes signs, I have a max or a min, local max or min. So a lot of things are happening at the critical points. So we have to test points around it. So a point between negative infinity and negative 1, I could pick negative 1,000, but that's kind of ridiculous because you're going to have to plug that in. It's much easier picking a nicer number, something like negative 2, 0, and 2. 0 is nice because it's really easy to plug in. Now, here is f prime. I'm going to plug in negative 2. Negative 2 plus 1 gives me negative. Negative 2 minus 1 is negative, but we square it, so it's positive. A negative and positive get me negative. I know that the derivative is always negative between negative infinity and negative 1 because it can only change signs at negative 1 and 1. Now plug in 0. I plug in 0 here, that's positive. I plug in 0 here, this is always positive because it's squared, and a positive times a positive is positive, so I know that's always positive. Now I'm going to plug in a 2. 2 here and a 2 here, that's positive. This is always positive because it's squared, so that's going to be positive. So I want interval of increasing or decreasing. So now I can say f is decreasing on the interval negative infinity to negative 1. Why? Because the derivative is negative on that interval. Now for the increasing part, I will talk about this real quickly. F is increasing on, you could break it up into 2 intervals. And say the reasons because f prime is positive on those intervals. Now, here's my claim. You could actually combine this into 1 because what's happening is it's increasing from negative 1 to 1, and then from 1 to infinity is always increasing, and there's a point where the slope's 0, but it's increasing through that whole region. So if you were to do negative 1 to infinity, in this case you'd be okay. We're going to look at the graph and see why, but we have another job to do. Notice, I'm going to graph decreasing, then increasing, and it continues to increase. There's a relative min right here. So you would say there's a relative minimum at x equals negative 1. Why? Because the derivative changes from negative to positive at x equals negative 1. So there's your relative minimum. And at 1, since the derivative doesn't change signs, you don't have either relative max or min at 1. And the justification is because the derivative does not change signs at 1. So let's look at the graph. The black line is a graph of my function f of x. And let's verify. It's decreasing all the way up to negative 1. Look, decreasing all the way up to negative 1. And then from 1 to infinity, it's always increasing because the derivative is always positive. So it's always increasing. Now notice at negative 1, you have a critical point, slope 0. And at 1, you have a critical point. But this one, the slope is 0, but it's increasing left and right. It didn't change directions. So therefore, you don't have relative max or min there. Now the red graph is the derivative. Now, from the red graph, you could figure a lot of stuff out, okay? And this is something you're going to have to be able to do. F prime is negative here. So we know the function is decreasing in that region, which it is. Then you'll notice the red graph is positive from there to there and positive there. So the function must be increasing through that whole region. The derivative is 0 there and there. Therefore, the tangent line must be 0 at those 2 points, which that matches. But look what happens. Right at that point, the derivative changes from negative to positive. Therefore, in the original graph, you have to have a relative min there, which you do. Derivative went from negative to positive. So it does have a relative min there. So these connections need to be made. Look at this red graph, and from that red graph, you should be able to get the black graph because multiple things are happening. The function is decreasing. The function is increasing. You're right. Decreasing, increasing. The derivative is 0 there and there. You're right. The derivative is 0 there and there. And at that point, the derivative changed from negative to positive, relative min at that point. So all that can be found from that red graph. And so, important, making connections between the graph and the derivative graph and the original function. All right, we have a couple more examples. We're almost done. So now we're going to do the same thing. We're going to find increasing, decreasing intervals, and we're going to find all the relative max and mins. So to find that, we need the derivative, and we have to do the product rule because we're multiplying two things. Here we go. We leave the first alone and take the derivative of the second. We take the derivative of the first, so I use the power rule, and leave the second alone. Now we notice they both have an x, so we're going to factor that x out, and we take the lowest power out. So we see that we have this -1 left, but we still have some x's left, but we need to figure out the power there. But, ooh, that's a 1/3, not a 1/2, sorry. But these two multiply to get that. Therefore, that exponent plus that exponent must equal 2/3. -1/3 plus what equals 2/3? That's going to be 1. And I should have taken that 1/3 out. So I'm going to take that 1/3 out. And you're going to say, this doesn't have a 1/3? Now it does. So I take that 3 out and that 3 out. That leaves me with a 3 and a negative and x to the first. So I take that 3 out and I take that whole thing out. So I'm left with a 2 minus x. Okay, on top, well, this is going to move to the bottom because the negative exponent. And that 3 is already on the bottom, so it stays on the bottom. We combine like terms. That's going to be minus 2x minus 3x. That's minus 5x, and that's going to be 4. 4 minus 5x. There is my derivative function. Okay? We will keep going. We need to find critical points. Well, that's going to be when this equals 0. It equals 0 when the numerator is 0. And we solve for x, we're going to get 4/5. But when the denominator is 0, my derivative will be undefined. Divide both sides by 3. Cube both sides. So we end up with 2 critical points. So we got to find out what's happening around those points. So we are going to make our number line table. 2 critical points, 0 and 4/5. We're going from -infinity to infinity, and x and f prime. Again, if you're memorizing this table, you don't understand. You need to understand why this table. It needs to make sense. If it's not making sense, you need to ask questions. You need to figure out what's going on. I'm going to pick numbers in each region, which seem nice to me. I'm going to evaluate the derivative on those regions. So I'm going to plug in -1. If I put negative there, that's going to be positive on top. And negative, That's going to be negative because you take the cube root of a negative, it's negative. So that's going to be negative in this region. I'm going to put a minus sign there. Plug in a half. If I put 1/2 there, that's negative 2.5. 4 minus 2.5, that's positive. And 1/2, cube root of 1/2 is positive. So we're going to be positive in this region. And then I'm going to plug in 1. 4 minus 5 is negative, so the top's negative. I plug in a 1, that's positive. So we're going to be negative in this region. All right, so what do we have? F, oh, it's G, not F, sorry. G is, that's not how you spell is. I'm getting tired. It's really late right now, guys. Let me fix all this. G is decreasing where? From negative infinity to 0 and 4/5 to infinity because the derivative is negative. Whoa. Is negative less than 0. You can write is negative on those intervals. Then you have to say G is increasing on the interval from 0 to 4/5 because G prime is positive on that interval. Now, what else is happening? At 0, look, let me draw. It's going to decrease, then it's going to increase, then it's going to decrease. That's just a general idea. So what's happening here, you're going to have a relative minimum because the derivative changed from negative to positive. So G has a relative minimum or a local minimum at x equals 0. Why? Because G prime changes from negative to positive. And you'll say G has a rel max, relative maximum, at x equals 4/5 because G prime changes from positive to negative. And again, you shouldn't have to memorize that. You should visualize. Oh, increasing, decreasing, relative maximum. So that is my evaluation of this. Let's look at the graph. Black is the actual graph. It's decreasing all the way up to 0. That's what this is saying, up to 0. From 0 to 4/5 increasing, 0 to 4/5 increasing, and then after that, always decreasing. So it matches that. What happens at 4/5? The derivative is 0 at 4/5. Look, at 4/5, tangent line 0. What happens at 0? You're dividing by 0. It's undefined. Well, we have a sharp point at 0. Derivative does not exist at a sharp point. So at 0, that's showing us we have that sharp point there. Now, we said there's a relative minimum at 0 because the derivative changed from negative to positive. That is verified here, relative minimum there. The derivative is positive to negative to positive. And right there we have a relative max because the derivative changed from positive to negative. All right. Let's evaluate the derivative. So the black graph is g of x. The red graph is g prime of x. But from g prime, you should be seeing stuff. Look, that is negative because it's below the x-axis. So the function should be decreasing in that region, which it is. The derivative is positive on that region because it's above the x-axis, so it should be increasing, which it is. And from here on, the derivative is negative, so it should be decreasing, and look, it is. And at that point, the derivative changed from positive to negative, giving you relative max there, which we have. And at this point, the derivative changed from negative to positive, giving us a relative min, negative to positive. So all that fits. You need to look at this, process it, and have it make sense to you, okay? So that is relative max and mins. And here's one last one to look at. This again is very logical. So don't memorize, just have it make sense. F is continuous and there's only one local max or min. Only one local max or min. Well, if there's only one relative max, it's actually an absolute max. And if there's one relative min, it's actually an absolute minimum. So I'm just give you a quick drawing of that. So we have an interval. There's only one relative max or min. Clearly that has to be absolute max. There can't be any bigger point than that. And similarly, there's only one relative minimum point. That's got to be the absolute minimum. Because if there's only one, it has to go from decreasing to increasing. It can't decrease again and get lower than this point, or else you'd have another critical point, another local maximum or minimum. So basically, if you only have one local max or min, it only changes direction at that point. That point here has to be a maximum because it can't change directions again, or you have another relative extrema. So if you have only one relative extrema in a region, that will be an absolute extrema. That's all it's saying. So looking at this, let's take the derivative, 3x squared plus 4x, factor out an x, you're going to get 3x plus 4. You set that equal to 0 to find the critical points. X equals 0, 3x plus 4 equals 0, x equals negative 4/3. But look at our domain. This is out of our domain, so we only have one critical point. So if that critical point is a relative max or min, it is absolute max or min. So we're going to test around that point. Here's our number line. Here's our 0. Now, this is important. Okay, our left endpoint is -1. Our right endpoint is 1. That's given. So I'm going to do -1/2 and 1/2. And we want to find if this is a relative max or min. Plug in -1/2. That will be negative. -1/2 times 3 plus 4, that's positive. So that's going to be negative in that region. Plug in +1/2. That's going to be positive. That's going to be positive. So we're going to have positive. Look, the derivative changed from negative to positive. Decreasing, increasing. That is a relative min. So there's a rel min at x equals 0 because f prime changed from negative to positive. But it's also an absolute minimum. We have an absolute minimum at x equals 0. Why? Because x equals 0 is the only relative extrema. And if you look at this picture, our critical point was at 0. That's where the derivative was 0. And this is the actual graph. That's an absolute minimum. Because it's the only relative extrema, there can't be a lower point. Again, to be a lower point, you'd have to change directions to get lower, but you can't change directions or you have another relative extrema. So if you have only one relative extrema, it has to be the absolute max or absolute min. And that's it for this lesson.